Okay, 9 o'clock. Time to start. Does anybody have any questions about anything before we start? Fortunately, got the iPad back. Well, I always had it, just the internet is properly working now. Apparently, the whole school had some issues between Friday and Tuesday. So, nursing was down too. Okay, so we left off talking about oxidation states. So, oxidation reduction reactions, basically transfer of electrons. What is oxidized means losing electrons. What is reducing means gaining electrons. So whenever oxidation happens, reduction happens, and vice versa. So how do we keep track of electrons? One of the ways we can do it is with the oxidation numbers, oxidation states. And these are important. To give you an example, chromium. So chromium metal, very safe. You can wear it. I have a ring that's 304 stainless steel, has chromium in it. Chromium plus 3, oxidation state plus 3, totally fine. You can use it as a paint. You can see it in paints and walls. Chromium plus 6, really, really nasty stuff. It's a carcinogen. It gives you a skin rash and gives you cancer. So that's the oxidation states. So oxidation states do matter, and they change, and the chemical and also, in certain cases, biological issues of oxidation states dependent on the oxidation state. Okay, so here are the rules. Free element is 0. Monatomic ion is a charge. Sum of a neutral molecule or ion is, well, neutral molecule is 0. Ion equals a charge. Alkalis plus 1, alkaliners plus 2 in compounds. Obviously, if they're free elements, they're 0. And then for all else, this chart here, fluorine tends to be -1, hydrogen plus 1, oxygen -2, halogens -1, oxygen family -2, nitrogen family -3. And we applied it for this example here. So let's do this for a bigger compound, potassium dichromate. So this is, use the rules here, so 0, the sum, rule number 3 is 0, is 2 times potassiums plus 2 times chromiums plus 2 times oxygens. So start assigning numbers. Potassium is an alkali, that's plus 1. Oxygen tends to be -2. So 0 equals 2 times plus 1 plus 2 times oxidation number for chromium plus 2 times -2. So -4, 2 times -2 is -4 plus 2. I'm sorry, it's 7. What am I doing the 2 for? 7, sorry. 7 times -2 is -14, plus 2 is -12. So 0 is 2 times chromium -12. 2 chromium equals 12. Chromium is 6, plus 6. So this is plus 1, plus 6, -2. And that's the terrible plus 6 hexavalent. So if you hear the term hexavalent, so hexavalent versus trivalent. So if you hear those terms, trivalent means plus 3, hexavalent plus 6. This is the nasty stuff. Have you ever seen the movie Aaron Brockovich? That's this stuff. That's this stuff right here. Okay, let's see if you follow. What is the oxidation number in manganese and potassium permanganate? I just put OX for oxygen because my 0 is the same thing as my letter O. Some people think it's A, 0. I think B, 7. How many think C, 8? I think D, 14. Who's stuck? I'm going to come around anyways. All right. Zero, this whole thing is 0. Well, I mean, you start sending out alkalines, that's 1, that's potassium, here's the chart. Yeah, that's it. Okay. So here's the rules. Only 3 neutral molecules only the sum of all states, and neutral only when 0 is right? So this is a equals 0. It's potassium to manganese, and 4 oxygens.
Why is it 7 and not -7? Because I give to the -8 plus 1. Shouldn't that be -7? That's -7.
Mn minus 7 is, then you add 7 to both sides. So Mn has to be plus 7 by that algebra expression.
So 1 plus Mn plus -8 here.
Yeah.
That, this, I got there, but this has me.
Yeah. If you have -7 minus 7, that's -14.
But where's the other 7? There's only one 7. We're doing it to both sides to get rid of something? Is that what you're saying?
No. So you got that. You understand this.
Mm-hmm. Absolutely.
Okay. And okay, so potassium alcohol plus 1, that's -2 for oxygen.
Mm-hmm.
Right? So plus 1 minus 8 is 0 is Mn minus 7.
Mm-hmm.
Right? So you add 7 to both sides, and you get 7 equals negative.
Thank you.
Yeah.
It was the adding it to both sides. I dropped that step. Thank you.
Yeah. Okay. Everyone seems to be converging. It is 7. All right. So next thing is to talk about oxidizing agents and reducing agents. So, and students actually get confused about this sometimes. So what's confusing about it is whatever is oxidized is the reducing agent, and whatever is reduced is the oxidizing agent. So I think about James Bond. I've been watching lots of James Bond movies, and you know what? He never dies, right? He's always killing people, though. So James Bond delivers the death, but he himself never dies, right? So it's what you deliver. So if I'm going to deliver oxidation, how do I deliver oxidation? I deliver oxidation by taking electrons. So if I'm going to oxidize something, I'm going to take electrons. Now I have electrons. So by the act of taking electrons, though, I've become reduced, right? So how does something deliver oxidation? It itself grabs electrons and then it becomes reduced. And something that's a reducing agent, how do you deliver a reduction? You give electrons away. Oh, you want to be reduced? Here's some electrons. So you want to be reduced? Here's my electron. I'm giving you my electron. I'm the deliverer of the reduction. I'm the reducing agent. But by the fact that I've given up electrons, or an electron, electrons, I've been oxidized. So the species that is oxidized is the reducing agent, and the species that is reduced is the oxidizing agent. So it's what you deliver.
Can you say that one more time?
So the species, compound, whatever, that is oxidized is the reducing agent. It delivers reduction. And the species that's reduced is the oxidizing agent. So to give you an example here, we have magnesium plus 2 waters yields magnesium hydroxide and hydrogen gas. So over here, if we assign the oxidation states, magnesium is a free element and oxidation state is 0. So water, neutral compound, hydrogen is +1, oxygen -2. So magnesium hydroxide, magnesium is an alkaline earth and a compound, it's +2. O and H are still -2, +1. And hydrogen gas here, this is a free element, its oxidation state is 0. So what is going on in this chemical reaction is magnesium is giving electrons, so it's giving 2 electrons to 2 hydrogens, and the hydrogens then become hydrogen gas and they leave. So magnesium is losing 2 electrons, the hydrogen, water, the electrons are transferred to water, water is gaining electrons. So magnesium is being oxidized, water, specifically hydrogen in water, is being reduced. So since this is oxidized, it's delivering reduction, it's the reducing agent. And water here, it is being reduced, which means it's delivering oxidation, it's the oxidizing agent. Does that make sense? Okay. Let's see if you can figure this out. Respiration of glucose. C6H12O6 plus oxygen makes water and carbon dioxide. What's the reducing agent? How many people think it's A, glucose? I think it's B, oxygen. I think it's C, water. D, carbon dioxide. Well, they're products. They can't do that. So it's one of the reactants. So what else? You probably want oxidation states. Glucose, carbon happens to be 0. Hydrogen is +1. Oxygen is -2. Oxygen here is 0, +1, -2. +4, -2. Those are the oxidation states. Some people think A, glucose is a reducing agent. I think B, oxygen is the oxidizing agent. Okay, reducing agent. Okay. So let's track to see where electrons are going. Carbon here is going from 0 to +4. What is carbon? What's happening to it? Is it being oxidized or reduced? It's losing electrons. What does losing electrons mean?
Oxidized.
Oxidized. Oxygen is going from 0 to -2. So what is happening to oxygen? So
Being oxidized.
no, it's being reduced.
0 to -2.
0, yeah. So remember, electrons are negatively charged. Going from 0 to -2, that means you've gained electrons. So oxygen is being reduced. So the substance that delivers the oxidation is the reducing agent. So it's glucose. Glucose is the reducing agent. So a couple ways you could figure this out other than carrying out all the numbers going on through. One of the definitions of oxidation is adding oxygen. You are literally adding oxygen, right? You have fuel plus oxygen. You are literally adding oxygen, right? So adding oxygen is a definition of oxidation. That's one way you could figure that out. The other thing is, do you remember what I said, what the most common reducing agents were? They're fuels. Fuels are the most common reducing agents. And glucose is a fuel. It's our primary fuel. It's us humans' primary fuel. So, of course, the most proper is to look at all the oxidation states and then track to see where the electrons are going. In this case, glucose is giving electrons to oxygen. So glucose is losing 6 electrons, and then the electrons are being taken up by the oxygen. So I guess that would be C6H12O6. That would be 6 CO2s and 6 waters. So you would need another 6 oxygens there. So, okay. That means that carbon is losing 24 electrons and the oxygen is gaining, 6 times 4, 24. Oxygen, each O2 is gaining 4 electrons. So, questions with this? You seem a little lost. Yeah, go ahead.
Why is the on the side of that equation, the oxygen, it has a 0?
I'm giving that the oxidation state. It's a free element. O2, that's an element, right? A oxidation state in an atom and a free element is 0. So, right, examples, metal and Cl2, 0. Other questions? Susie, I'm confused again. Let me try to explain it one more time. So it's kind of like the opposite. Remember James Bond? Okay, well maybe we'll pull back into the age of Britney Spears, right? So you heard the song Womanizer. So if a man is a womanizer, is he a woman? No, he's still a man, right? But he engages in the womanization, right? So, and oxidizing. So if I'm being oxidized, I'm the reducing agent. So it's kind of the opposite like that. So, okay, well, pretend my water bottle is an electron. So I am going to be oxidized. So I'm going to deliver reduction to the desk. I have now reduced the desk. The desk has been reduced. I'm the reducing agent. But I lost my electrons. Since I lost my electrons, I'm oxidized. So the species that is oxidized is the one that's delivering the reduction. Glucose is delivering electrons to oxygen. It's delivering the reduction, but what's happening to it? It's being oxidized. Is that making sense? Or okay, I still get confused looks. Okay, but we are done with the testable material for this test. I will review the test on Monday. I'll come up with some sort of review. But I will move on to gas laws now, unless anybody has any questions. So we'll move on to chapter 6. But I will come back to this beforehand, and then the test is a week from today. And I haven't written it yet, but I'll write it soon, and you can ask me questions on Monday about it. So, okay. Question though. I don't know how to scuba dive, but I like to snorkel. Would this work? Would this be okay if I had like a 105-foot snorkel, put buoys around it, and had a really, really long snorkel, and if I went down 100 feet, and could I breathe through this snorkel? Why not? Pressure, yes. You're feeling the pressure. So 100 feet of water, each 33 feet of water is the same as an atmosphere. 33 feet of water is equivalent, more or less, to the average atmospheric pressure of the Earth. So that means that there is an atmosphere of pressure here, and then on my lungs here, there is an additional 3 atmospheres. So this pressure is 3 atmospheres. So that means on my lungs there's a pressure of 4 atmospheres. And up at the snorkel, there's 1 atmosphere. So where does gas flow? Does gas flow from high pressure to low pressure, or from low pressure to high pressure? It always goes high to low. So flow, when you have fluid flow, it goes from high pressure to low pressure, high temperature to low temperature, or high concentration to low concentration. So we always flow in that direction. That's also because of entropy. We're going to talk more about entropy a little bit this semester in the next chapter, much more in detail in Chemistry 162. Right? So entropy is disorder, and the universe never really self-organizes. At least it can, but it's very improbable. It's probability. So when you walk into the classroom, you don't worry that you're going to come into a vacuum with all the air in the corner. The air is going to be spread evenly. So same thing with flow. If you have a high concentration of something, it's going to flow towards whatever the low concentration is. And if you have 4 atmospheres of pressure pushing down in your lungs, and you try and breathe in air that's 1 atmosphere, your lungs are going to collapse. So this will not work. Trying to breathe will push all the air right out of your lungs. And people said this before, is pressure. So what is pressure? So pressure definition is force, a force over an area. So a common pressure unit that we use for tires, like car tires, PSI. What is PSI? It's pounds per square inch. PSI, which means that if you have a square inch, so a surface area of square inch, that means you have 1 pound of pressure. So 1 PSI is 1 pound of force over a square inch. I know I'm using 2 fingers here, but I'm trying to illustrate. That's what a PSI is, 1 pound of pressure over a square inch. And other kinds of pressure, well, sound. Sound waves are pressure waves. They're also a certain type of wave called a longitudinal wave. So we'll talk about the longitudinal or transverse waves. We start talking about light. So a longitudinal wave means that the displacement is in the same direction of the traveling of the wave. So sound comes from my voice box, and it's coming out to you guys right now. And the air molecules, they're bouncing like this. A pressure wave, it's a shock wave, it's moving. The air molecules are moving back and forth, and they're moving back and forth in the same direction that the wave is going. So the pressure wave is moving that way. So the displacement of the pressure wave is the same direction as the wave is flowing, right? So so shock waves, same thing as sound. So if you have an explosion, and you can sometimes see shock waves going, what happens when a shock wave hits you? It blows you back in the direction of the shock wave, right? So that's a longitudinal wave. Transverse waves are the displacement is perpendicular to the motion. So the wave is going this way, displacement is perpendicular. So if you're in the ocean and a wave is coming at you and you're floating, what do? You go up and you go down. Where's the wave going? It's going this way. That's a transverse wave. And light is a transverse wave. So we'll talk about that in a future chapter. But sound, longitudinal wave, and it's a pressure gradient, change in pressure. And so where does pressure come from? So pressure is, it's the momentum, well, at least in gases. So, I mean, pressure, if I'm pushing down on the desk right now, I'm pushing down the desk, the pressure is coming from gravity, from my body weight. But in gases have pressure. So if I have a gas, like a balloon, I start feeling the pressure in it. Where is the pressure coming from? It's coming from collisions of the molecules. So molecules have a little bit of mass, they have a little bit of inertia, and so that little collision there is where the pressure comes from. So if you hit me with an oxygen atom, like, oh, hit me with an oxygen atom, like, doesn't matter, oxygen atom's not a big deal. If you hit me with a big number of oxygen atoms, like, I don't know, 6.02 times 10 to the 23rd, that's one of my favorite numbers, right? Then you can feel it. So 1 atom, 1 molecule, not a big deal. Something times 10 to the 23rd. Oh, now you can start to feel it. So little tiny bit of momentum from 1 molecule, not a big deal. Whole bunch of them though, oh yeah, you can feel the pressure. Okay. So, and I'm not going to go through all the, if you read the book, it'll tell you all about the different types of laws, and you probably did this in high school. I'm just going to jump right into the ideal gas law. But, okay, so Boyle's law. Boyle's law, and you're going to do a lab on this. Boyle's law states that pressure and volume are inversely proportional. So inversely proportional, that means when one goes up, the other one goes down. So an example of inverse proportion is like how much fun I'm having versus my bank account balance. Okay? So if I'm having a lot of fun, that means I'm taking trips, I'm going out, I'm buying things, right? It's fun to buy things. It's fun to go on trips. So what happens to my bank account balance? Going down. My fun level's going up though, right? Let's say I'm running out of money, so what do? Well, I'm gonna go home. I'm gonna start eating crock-pot meals at home, lots of ramen noodles, watch Netflix. What happens? My fun level's going down, but what happens to my bank account balance? It's going up. Spend all that money, like, you can survive for a while on ramen noodles. And my bank account balance creeps back up. So inversely proportional. When one goes up, one goes down, and then when one goes down, the other one goes up. So it's back and forth. And pressure and volume are that way. So if you blow up a balloon here on sea level, and you drive up to the top of Haleakala, what's going to happen to the balloon? Expands, right? Pressure goes down, so pressure goes down, volume goes up. So likewise, what would happen if I took that balloon and took it under 33 feet of water? It's going to shrink, right? Higher pressure, lower volume. So inversely proportional. Then, so that's Boyle's law. Charles' law. It's always weird because there's a Charles and then apostrophe S. Charles' law. That is volume and temperature are directly proportional. So an example of direct proportionality is like my happiness levels and your grades. When I'm very happy, everyone's happy. Everyone gets really good grades. And when I'm sad, I start taking on your guys and your grades start going down. No, I'm just kidding, of course. But you get the idea. Well, one goes up, the other one goes up, one goes down, the other goes down. So that means if you heat something up, the volume goes up, and if something cools down, the volume shrinks. So if you take a balloon, you blow it up, and you throw it in the freezer, it's going to shrink. An application of this is a hot air balloon. So we don't have hot air balloons here in Hawaii, but the way that they work is you have a droopy balloon, and then it's a hot air balloon because you heat up the air inside of it. They have little flames, and you can hear if you've ever seen that, and there's a flame that goes in it. And then what happens to the droopy balloon? It gets really big. So the air expands and fills the balloon, and then the hot air balloon can float by what's called buoyant force. So buoyant force, this is more a physics thing, but like when you float in water, so if you're floating in water, where do you float? You float up to your head, right, kind of thing, depends on, or your chest, depending on how dense you are. What is happening is the amount of water that you just displace equals your weight. So you will float to where the amount of fluid that you displace is equal to your weight. And water, and maybe you notice that salt water, you float higher in salt water because salt water is more dense than fresh water. And I've never been to the Great Salt Lake or the Dead Sea, and it's a brine solution. It's 25% salt. Apparently people float higher there. Has anyone ever been there? I've never been there. No? Okay. Take the word for it. If you have mercury is about 13.5 times as dense as water. You really can float very easily in mercury. Back in like the 60s and 70s, when safety was not an issue, there's photographs of people lying in pools of mercury, and they're like really flying on top of it. So you don't sink very far into a mercury bath. But okay, so that is a hot air balloon. That's Charles's law. But it also brings out something we call absolute temperature. So does anybody know the definition of temperature? Temperature is defined as average kinetic energy. So let me all write that down. So temperature, it's capital T is temperature, is the kinetic energy, Ke for kinetic energy, and a bar over something, that means the mean or average. So if you've taken math. So it's the average kinetic energy. So what's the difference then between cold pizza in the fridge and then warm pizza that you've heated up? What's the difference?
Breakfast and dinner.
Breakfast and dinner, okay. Yeah. So, what I was hoping you'd say was that on a molecular level, the warmer pizza, the molecules are moving faster. So, but this is beyond this course, but I think you should know this because it makes more sense. The true definition of temperature is average translational kinetic energy. So the word translational. Let me say right now, I am moving right now. I am moving very translationally right now. Can I move any other way? I can twirl. Right? Can I do anything else?
You can hula.
Hula? Yes, I can. I can hula. I can dance. So translational motion as a molecule. So Shaka, yeah, but water. So water temperature is this. This is translational motion. XYZ, right? So Cartesian coordinates. So moving around like this. This is rotational energy. This is vibrational energy. So those are the possible kinetic energies. Temperature is translational energy. So then, have you ever wondered how a microwave oven works? The way a microwave oven works, microwaves work by making molecules rotate. So here's water that's cold. It's moving very slowly translationally. You hit it with a microwave, put it in the microwave oven, what happens? They start to rotate. So, and this cold molecule that's rotating is moving, and it hits another molecule. So as it's rotating, it collides with another molecule, and its rotational energy is translated from molecular collision, translates into translational energy, right? So it's moving slowly, and then now it's not rotating as fast anymore. So it's moving very fast. Now this is heated up, and this has lost rotational energy. That's how your microwave oven works. It rotates the molecules, and then by molecular collision, it turns it from rotational energy to translational energy. And the same thing works for, so infrared light, when you feel something infrared, you can, oh, I feel the heat. It's making your molecules vibrate. So if you hit something, so water with extra vibration, extra infrared light makes it vibrate, and same idea, it's kind of hard to show, but it's vibrating, and then same thing is going to kick it and turn the vibrational energy into kinetic energy, so thus raising the temperature. Temperature is the translational energy, moving back and forth. So if temperature is average translational energy, and translational energy means things moving, so they're obviously, what happens when things are not moving? So here's something really hot moving around, here's something really cold. What do we call it when it's just not moving? Frozen, yeah, okay, good. Absolute zero. So what is absolute zero? Absolute zero is when things stop moving translationally. They're just not moving at all in space. That is absolute zero. So what's nice about temperature, so we have temperature and we have absolute temperature. So if you notice a few things, we have degrees Celsius and degrees Fahrenheit. the degree, what does it mean to have a degree? It means you relate it to something. So Celsius, the temperature Celsius, is related to water freezing at 0 and boiling at 100 at the average pressure of the Earth at sea level. That's what Celsius is based off of, right? And so it's a relative scale, and it's relative to frozen water at sea level. But absolute temperature is something we call Kelvin, named after Lord Kelvin, if you wonder. But Kelvin, 0 Kelvin means no motion, no translational energy. So Fahrenheit, although we use this quite a bit in the United States, Fahrenheit's a weird, what do we call it? It's a very strange system. It was designed so that human body would be at 100 degrees Fahrenheit, but it was based off of water freezing at 32, boiling at 2 and 12, and then brine freezing at about 0. So they chose that for Fahrenheit, and they're trying to make the human body temperature be 100 degrees Fahrenheit. Of course, it's about 98 to 99, depending on the person. So, of course, you say 98.6, but it depends on the person. Body temperature for Celsius is 37 Celsius, so if you're wondering. It also changes in the part of your body. So, like your hands typically are colder than your core, for instance. So, it's a range. But we have absolute on the Fahrenheit scale as well. It's called ranking. So R, if you see something that's R, the temperature is something R, that's the Fahrenheit scale, the absolute value of it. So absolute 0 for Celsius is at minus 273 Celsius. That's absolute 0. And absolute 0 in Fahrenheit scale is about minus 450 Fahrenheit. And it's always fun. Like I'm a judge for science fairs, and so some people's experiments are kind of cute. And I remember there was one student, he's saying, yeah, I look at this, and the temperature should be negative 10,000 degrees. He was so excited. And I'm like, yeah, you can't get to negative 10,000 degrees. So, because you can't get any colder than 0. You can't get any more motionless than not moving, right? So you can't go below absolute 0. So, if that makes sense. So you can't have, you have a limit to that just by the nature of what the definition of temperature is. Okay, so hopefully now you have a very good idea of what temperature is and how atoms and molecules store energy. We'll talk about this later again when we get to the electromagnetic spectrum, because different types of radiation do different types of things to matter. And microwaves makes matter rotate, and infrared light makes molecules vibrate. So, and there's a whole bunch of stuff with this, carbon oxidation for carbon dioxide, you can have something called a symmetric stretch. You can have an asymmetric stretch. You can have a bending mode. So there's a lot of things that happen between light and matter. So, okay, but definition of absolute 0, then an absolute temperature then. Kelvin is the degree Celsius plus 273.15. So if something is negative 100 degrees Celsius, what's the temperature in Kelvin? How many people think A173? Okay, good. Everyone seems to be following. So, right, plug in this equation. So Kelvin is minus 100 plus 273. This equals minus 173. Oh, no, sorry, not minus, plus. I just said you can't go below 0. All right. Questions with this? All right. There's a couple of laws. There's Gay-Lussac's law, for instance. There's Avogadro's law. Avogadro's law is volume is directly proportional to the number of moles, meaning if I add more moles to something, the volume increases. If I add more moles of air to a balloon, I will blow up the balloon, right? How do I blow up a balloon? I add moles of air to it. It blows up. That's Avogadro's law. And we can combine these together to form what is called the ideal gas law. So ideal gas law is stated as pressure times volume equals N, the number of moles, R, the gas law constant, and T, the temperature. So the gas law constant, depending on the units, the gas law constant has a value of 0.08206 for liter atmospheres over mole Kelvin. And the gas law constant is actually Avogadro's number times something called the Boltzmann's constant. So it's not really its own constant. It's a combination of two constants. And question?
What did you say R was?
The gas constant.
Constant?
Constant. Like being in a state of constant fear of chemistry. This is the gas law constant. It does not change. So, okay. But ideal gas, we'll talk about this more when we get to kinetic molecular theory. But the ideal gas, this is a made-up thing. This is actually a math model. This is the perfect gas. The perfect gas, what is the perfect gas? It's a gas that has a volume, but the particles themselves have no volume, and also the particles have no attraction for each other. Because what happens though in gases and real gas situations, you have particles that like to hold hands, and when you have two particles that are kind of hanging out, you have two particles here, and if they start hanging out together, these two particles more act like one particle, and in doing so, then the volume of the gas will decrease from the fact that instead of having two particles, we have one blob instead, and then the volume goes down, and that kind of thing. Okay, so and ideal gases, they work very well for high temperature and low pressure, and where we're at right now is considered high temperature and low pressure. So room temperature, this is high temperature, low pressure. What's low temperature? Minus 100 Celsius. That's low temperature. What's high pressure? 100 atmospheres. So surface of Venus, that's high pressure. So Earth surface is considered low pressure for the ideal gas law. And then because of that, when you use the ideal gas law, there's an error associated with your calculation. But we're not really talking about it in this class that much. So you don't have to worry about that. If you're an engineer and you're doing calculations, you have to worry about which model you use. And the ideal gas law is it's a good model, and it works very, very well for this temperature and pressure, on the order of 98 to 95-ish%. So it works pretty well. It's not perfect though, but we'll talk about the ideal gas law, where it derives from later. Okay, so ideal gas law. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmosphere and a temperature of 315 Kelvin. So remember, you say Kelvin, you don't say degrees Kelvin. It's 20 degrees outside. It's 293 Kelvin outside. So no degrees. Okay, so use the ideal gas law. PV equals nRT. And we are looking for the volume. So we solve for volume. So volume equals nRT over P. And how am I doing that? So it's fun to do math this way. So PV equals nRT, and I'm just moving P down there like that. Or I can multiply both sides by 1 over P, however you want to do the algebra. So solve for your unknown. Our unknown is the volume, is nRT over P, and then just put in the numbers. So we have 0.845 moles of gas R is 0.08206 liter atmosphere. Jeez, why am I can't spell atmospheres. I can't even spell the abbreviation for atmospheres. Mole Kelvin, temperature 315, over pressure 1.37 atmospheres. So let's look at the units. So the moles cancel there, right? So we're doing moles times 1 over moles. Kelvins cancel, 1 over Kelvin times Kelvin. And then we have this case here. Then you're dividing by atmospheres, right? So atmospheres in the top. So atmospheres in the top divided by atmospheres in the bottom. The atmospheres cancel. And our units are liters. So our unit-wise, it's liter. And whatever that is, put in your handy-dandy calculator. Okay. So 0.845 times 0.08206 times 315 divided by 1.37 equals 15.9 liters. 15.9 liters. Oh, that's right. I can't use my Apple Pencil on my Android phone. And there's the calculator. So 15.9. All right, recap for this one. We are given the number of moles, the pressure, and the temperature, and we want to know the volume. So PV equals nRT. We solve for the volume by dividing both sides by pressure. So volume is nRT over pressure. And then we just plug in the numbers. Units cancel to liters, and the volume is 15.9 liters. Questions with this one? Okay. Pressure is 0.5 atmospheres. Volume is 50 liters. Temperature is 50 degrees Celsius. What is the number of moles? Oh, I didn't give you R. I'm going to think A, half mole. I'm going to think B, 1 mole. I'm going to think C, 3 moles. I'm going to think D, 6 moles. Oh, no one fell for the trick. Ah. What's the trick? Temperature needs to be in Kelvin. But most people are actually going for B, and B is the right answer. And that tells me you get this concept. Does anybody need this explained, or? If you do this, you get about 0.9. Is that the my calculator say? So with 1 sig fig, that rounds up to 1 mole. So, but you guys good? Questions with this? All right. Oh, derivations. I hate derivations. So here we're going to derive something, and it's always kind of awkward when you first start doing this. So some things. So molarity. This is moles per liter. This and N is number of moles over liter. So N is number of moles and liter is a volume. So we say that concentration is N over V. And if you look at PV equals nRT, and what is N over V? So that means we have to, so if we can take the N and put it over here. Wait, no, wait. We got N over V. We got it backwards. We want to have N over V. We move the volume over here. And that means we have to have RT in the bottom. So move RT. Oops. Lost half my R. Okay. So rearrange it this way. So N over V is P over RT. It's fun. I like doing math that way. So are you good? Do you guys follow how I was doing the math? Hopefully you're following that. And density, what is molar density? Definition of, so density, mass density is mass over volume. So molar density is moles per volume. So moles per liter is molar density. So here, moles per liter is molar density, then times grams per mole, that's the molecular weight, is density is grams per liter. So molar density times molecular weight, times grams per mole. And you can take this molarity, moles per liter, N over V, and you can set that, okay, N over V, density. So grams, so this, wait, I'm copying. This grams per liter density is equal to the molar density times grams per mole. So then you set this equal to each other. You set this here. It's hard to see. N over V is equal to, oops, that's it. I feel like I'm fumbling through the molecular weight. So, density. Yeah. The molar density, the N over V, times the molecular weight, grams per mole, equals the density in grams per liter. So and we set this up here, m moles per liter is pressure over RT, and density is equal to the moles per liter times, I'm doing this, the molecular weight. So that means that, and since we've already established this, capital M equals P over RT, so that means density is equal to P over RT times the molecular weight in moles per liter. Okay, fumbling through that. And that we've defined density, we can use this to calculate some densities. And before I move on, let me talk about pressure units. So we, at least here in the United States, we use 1 atmosphere a lot. I should say frequently, it's better English. We use 1 atmosphere frequently in the United States. That's our standard state is 1 atmosphere. There's a couple other pressure units we use. 760 millimeters of mercury. If you've ever looked at, like if you get a weather report, it'll say, what is the barometric pressure? And usually it's in inches of mercury. So it's about 29 inches. So I already mentioned that the atmosphere, the pressure from the atmosphere is from 33 feet of water. Okay, so what does that mean? So we're at about sea level right now, and from here to what's considered outer space is about 60 miles. Okay, so if you look at the weight of the atmosphere from here up to about 60 miles, and the air, of course, as you go up, gets thinner. But if you take the weight of all that air coming down to about right here, that amount of weight is about the same amount of weight as 33 feet of water, which is about 10 meters of water. And it's also equivalent to 760 millimeters of mercury, which is about this much mercury. So if you have about this much, and mercury is about 13.5 times as dense as water. So that's why this much is the same thing as 33 feet. So this much mercury is the same. If you were to have a vat of mercury, if you stuck your arm this far into the vat of mercury, that'd be the same as 1 atmosphere of gas pressure here on the Earth. So, and it's the weight. It's from gravity. And so my college chemistry professor, I remember, and we're still friends, he told me a story of how at Kodak, when they actually made film, that they had a lot of mercury, and one of the things they told you to do is like, oh, we have this 55-gallon drum of mercury. Why don't you try sticking your arm in it? And I guess people would stick their arm in it. It would be really hard to go in there, and they fly out because it's so dense. The mercury is so dense. And he told me it felt so weird because when you stick your arm in there, because there's so much weight, and it makes your hands feel really weird from all the pressure of just sticking it down. I mean, it's the same thing as, like I said, being under 33 feet of water. Can you imagine that? So that's going to hurt in a way, right? So, but okay, so these are where the different pressure units come from. 1 atmosphere is the same as 760 millimeters of mercury, or about 29 inches of mercury. We don't use inches of mercury here in chemistry class. Also, millimeter mercury is the same unit as something called torr, capital T-O-R-R, same unit. It's about 10 meters of water. It's also 14.7 psi. It's also 101.3 kilopascals. So the Pascal is the SI unit, so System International Metric System. That is the SI unit for pressure. And a kilopascal, what is a Pascal? A Pascal is a pressure of 1 Newton, so force, so pressure is force per area. It's 1 Newton of force over a square meter. So pound per square inch. Pound is actually a fairly strong force, right? So I mean, pound's pretty serious amount of force, and square inches are kind of small. So square inch is not very big. A Newton is nothing. A Newton is a kilogram in gravity. So this is about a liter of water. So gravity is 9.8 meters per second squared. So this 1 kilogram of water in gravity, this thing has a weight of about 10 newtons. So, or a force, I should say. A force of 10 newtons. And if this force so divide it by 10, and then put it in an area of a square meter. So this is this tabletop here. Well, I guess your tabletop's about 3 square meters. So take the weight, 1/10 the weight of this water bottle, so about 1/10 the amount of water, and you pour it out over 1/3 of the desk. That's not a lot of force, right? That's not a very high pressure. So that's 1 Pascal, and an atmosphere pressure is 101,000 pascals. So in Russia uses, for their standard state, they use something called a bar. A bar is 100 kilopascals. So 100,000 pascals. And we use an atmosphere, which is 101.3. I think the Russians have a better standard state than we do. So we have it based off of the average of the Earth. They actually have a derived unit from something that makes more sense. And this is important because since the end of the Cold War, the United States and Russia have been collaborating, especially in the International Space Station. And we use different states for things. So even though theirs makes more sense, what we've done is we flexed our United States muscles, and now they use our system instead, even though theirs is better. But hey. Oh, well. Okay, so other things from this, so 14.7 psi, 15 psi. So if you ever do calculations, so firefighters do calculations like this on the fly all the time. So let's say I want to put out a fire and I need to shoot water 100 feet in the air. So if I want to shoot water 100 feet in the air, how much pressure do I need to put on the hose to shoot water 100 feet in the air? The answer is 45 psi. So 100 feet is 30 meters. So 33 feet is 10 meters. So 100 feet, it's 3 atmospheres of pressure. And an atmosphere pressure is about 15 psi. So if I'm a firefighter and I'm like, okay, that's about 100 feet. All right. When they in the fire trucks, what are they? They're pumps. I mean, they have ladders and they have a pump in them, right? So you connect the fire hose to the truck, and the truck comes out, and then you have a couple people holding it. You're like, okay, so I need to shoot that up. I need 45 psi, and I'll probably need 3 or 4 people. Like, hey guys, come over here. I need 3 of you to hold this hose as we shoot water at the fire. That's 100 feet over that way. So that's how they do calculations, like on the fly for firefighters, if you're ever wondering. They're not like, well, little higher, little higher, little higher. Oh, it's too much. No, they've already figured that out. They know, like, okay, that's about 100 feet, and then, I need that much pressure, and they do these calculations real fast. Plumbers the same way. So stories of buildings, I want to know how much of a pump I need to pump water up to the top story. I can do that by every 100 feet requires 45 psi kind of thing, or like the 33 feet is 15 psi. They use those units for pumping water up high. Also, water coming down that way. How much pressure am I going to have? So for water towers, so if you have a water tower and I want to know what's the pressure in the faucet down here, I can do it by the height of the water and gravity. So we do it for water pressure, not just gas. These all work for water as well as gases. Pressure works the same way. Okay, so we did that horrible derivation, and I'm going to apply it. Calculate the density of nitrogen gas at 125 degrees Celsius at pressure of 755 millimeters of mercury. So already have that equation there. Density is pressure molecular weight times or divided by RT. So our pressure is 755 millimeters of mercury, and then an atmosphere is 760 millimeters of mercury. So there's the pressure. Molecular weight of nitrogen is 28 grams per mole. and I'm getting that from over here on the periodic table. And then R, 0.08206 liter atmosphere over mole Kelvin times temperature. So Kelvin is degrees Celsius plus 273.15. So that is going to be 398 Kelvin. 0.15 I know, but you don't have the other units, so you're not really sure. So what is that value? 755 divided by 760 times 28 divided by the quantity 0.08206 times 398. And it is equal to 0.851 grams per liter. So if you look at the units, millimeters of mercury cancel, atmospheres cancel, 1 over moles cancels, kelvins cancel, and we're left with grams per liter. And let me take a picture of this. Okay. So our answer is, again, 0.851 grams per liter is the density of air at 125 degrees Celsius. So that's not much. So about a gram per liter. So water, the density of water is 1 kilogram per liter. So density, it's 14.
What did you do with that?
This is the M. So molecular weight, nitrogen, density of nitrogen gas. Nitrogen is N2.
And you doubled that because of the 2 to get your 28.
Yeah.
Thank you.
Okay. So density of nitrogen, it's a little hot. It's hot nitrogen, but it's about 1 gram per liter. Compare that to water, which is a kilogram per liter. That tells you something about gases, right? Gases, there's not a whole lot of matter to gas. So when you're in water, so when you're swimming, I like to swim, right? You can feel that water when you're pushing it. You're like, ugh, I'm pushing the water. And it propels you forward really, really quickly. So you do this in air, it's easy. You go into water and flap your arms. This is really hard. In air, it's easy. Because why is it so easy? Because there's not a lot of matter in air. Why do we have those huge windmills on West Maui? Why are they so huge? Yeah. And why do you need a big surface area? Because there's not a lot of matter in air. There's not a lot of momentum to be transferred. So you need big fins. Have you ever seen a hydroelectric plant before?
Mm-hmm.
They're tiny. They're really, really tiny. They're maybe a quarter the size of this room. At least the turbines, they're very small. Why are hydroelectric plants so small? Because there's so much matter in water. And you don't need a lot of water to turn a turbine to generate electricity. Whereas windmills, you need really big windmills to generate a little bit of electricity. So, okay. And I think we're just about out of time. Yes, we have 1 minute left. So, well, recap for this one. We calculate out the density, use the equation. Density is pressure times molecular weight over RT. The new skill in this is the conversion of the pressure units. And then we get 0.851 grams per liter density, which is not very high. And so that's not very high. Okay. All right, I will See you guys on Monday.